Okay, for topic three, we're going to look at proving or establishing trig identities. Okay, so we're basically going to be given a statement that is true, and we have to show that it is true. Okay, now, just like with the previous topic where we were looking at ways to simplify expressions, we gave you some tips, some steps that you can try, but sometimes you just have to try things and see how it goes. Okay, so there's not always a step one, step two, step three, step four. Okay, for these types of problems, you just have to try something and you have to be willing to try and try again. Okay, so use pencil, give yourself plenty of space, and if you try something and it doesn't really go anywhere, start over and try something new. Okay, so we do have in parentheses here, this is a general approach and may not always work for every problem. However, this is a good starting point. Okay. So, some things that you always want to do, start with the hard side. So, you're generally going to have, well, you're definitely going to have two sides of like an equation, and one's going to have just more pieces to it. It's going to have just more going on. You want to start there, and you want to show that the harder, nastier side equals the simpler side. Okay. And so, when you're doing this, if you have like multiple fractions, you want to try to get it equal to just, or not equal, but make it into just a single fraction. Okay, so start with the harder side. If necessary, try to get it written as a single fraction. It is also really helpful that if possible, try to write things in terms of sine and cosine because things with sine and cosine can be really nice, easy to work with. Okay. Use known identities. So those fundamental identities of trigonometry that we have on the first page of this note set, think about those, okay? See if you can use those or find ways to manipulate those to where they do work for you, okay? Try to work on just one side of the identity. So again, you're going to look for the side that's kind of the nastier side that's just got more going on, and you want to stick with that and keep doing steps to that until you simplify it all the way and it equals the other side, okay? And then make sure to leave plenty of space to work with. So in these worksheets, the first one I didn't give you as much space because they're not gonna be as long, but I did try to give you lots of space to work in, okay? And please, 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 just get in the habit of using pencil with this stuff. I can't say it enough. Like use pencil, be able to erase, start over, give yourself plenty of space. I would also say start on scrap paper, and then once you get it worked out correctly, then move it to your official lab paper or homework paper or whatever. Okay. So again, we've given you some steps to try. Do what you can with them. One step I do see now that I forgot to list or mention is try to work on just the one side, which I mentioned that, but don't move terms around from left to right. Okay. So keep it all on one side and do what you can to simplify it using all the tips that we learned in the previous video and then these identities. Okay. So for example 3, it says prove each identity. You'll have some people say establish these identities. It kind of means the same thing. So we have for part A, secant theta times sine theta equals tangent of theta. Okay, so we can take it at blind faith and be like, sure, it's true, but let's prove it's true. Okay, now you always want to start with kind of like the more complicated side, the side that has more going on. So for us, that's going to be the left here. We want to show that secant of theta times sine of theta really does equal tangent of theta. So we want to work on the left-hand side and do different things until we get it simplified and show that it really does equal tangent of theta. Okay. So if possible, you want to try to get things in terms of sine and cosine. That's always going to be nice. If you get stuck, see if you can rewrite things as sine and cosine. And I really like the idea of rewriting secant. We know that secant is the reciprocal of cosine. So secant is equal to 1 over cosine. So let's rewrite it as such. So secant of theta is equal to 1 over cosine of theta. So this is already a known identity. This one we know is true, so we can use it. And so we've got secant of theta, which is now really 1 over cosine of theta times sine of theta. Okay, well, great. Now what? See if we can write this as a single fraction. Okay, that's one of the tips in here. Start on one side of the identity or one side of the equation, and then if necessary, try to write it as a single fraction. We can do that here. If I think of sine of theta as sine of theta over 1, I can just multiply across. 1 times sine of theta is sine of theta, and cosine of theta times 1 is cosine of theta. Well, that's great. Okay, so we've done this now. And then you want to think, is this equal to something that we know? Well, if we go back to our list of fundamental ideas, hopefully you're at home screaming what this is equal to. But if we go to our list of fundamental identities, we had the quotient identities, and we were told right here that tangent of theta is equal to sine of theta over cosine of theta. And that is exactly what we have down here. So we can now say, okay, we got the left side to equal tan of theta, And so now we can drop this down and say, hey, these two things are really equal. So the left really truly equals the right. So we were able to show that secant of theta times sine of theta really does equal tangent of theta. Okay, let's look at part B. So for part B, I have secant theta, or secant of theta minus 1 times secant of theta plus 1 equals tangent squared of theta. Okay, so that's a lot. Let's see what we can do. So we're going to start with the left-hand side. There's just kind of more going on with the left-hand side. So can we show that secant of theta minus 1 times secant of theta plus 1 is equal to tangent squared of theta? And what I would do here is maybe look at simplifying this. Earlier when we were in topic 2, we reminded ourselves of this idea of conjugate pairs from back in 171. And we said if we were dealing with like the complex numbers, if we were dividing complex numbers, the tip that we use, the trick we use is we would multiply the numerator and denominator by the conjugate of the denominator. And this was really just equal to 1. So this was just 1. So we weren't changing the value, but we were using it because multiplication of conjugate pairs simplifies really nicely. Okay, so if you have something that looks like conjugate pair-ish, try multiplying, see what happens. So let's scroll down here. So I notice I have secant of theta minus 1, and then I have secant of theta plus 1. And that's kind of the format of conjugate pairs. You have these two things, you add, and then you subtract. So let's multiply. So you can do the full like FOIL method where you multiply each thing in the first set of parentheses by each thing in the second, or you can take the shortcut. I'm going to multiply everything out just to prove to you that things simplify nicely. So we want to take secant of theta times secant of theta. Well, that becomes secant. Let me go back to the black ink. So we have secant of theta times secant of theta is secant squared of theta. And then I have secant of theta times 1, which is just secant of theta. I'm done with secant of theta. I want to come pick up the negative 1 and do the same thing. So I have negative 1 times secant of theta. That's negative secant of theta. And then I have negative 1 times 1, which is negative 1. Okay? So what we notice here, hopefully, is that secant of theta minus secant of theta, that just becomes 0. And what I'm left with is secant squared theta minus 1. Now, anytime I have a trig function squared and then a plus or a minus 1, I always think Pythagorean identities, okay? So anytime you have a trig function squared with a 1, go and see if you can play around with your Pythagorean identities. So let's mosey on up to page 1. All right, so with our Pythagorean identities, the great news is tangent and secant go together. So is there a way that we can rewrite this Pythagorean identity so that it kind of works for us? Well, what I have in the page below was secant squared theta minus 1. Is there a way to rewrite this Pythagorean identity so that I get secant squared theta minus 1? And the answer is absolutely. I can subtract 1 from the left and then from the right, and what I get is tan squared theta equals secant squared theta minus 1. Well, this is exactly what we have in our example down here. So we know that secant squared theta minus 1 equals tangent squared theta because this is already an established identity. We know this is true, okay? So we can come back down here and we can say, okay, well now secant squared theta minus 1 is just tan squared theta. And at this point, I can bring down my right-hand side and I can say, hey, these two things are equal, okay? So we've established that these things are really true. So secant theta minus 1 times secant theta plus 1 really does equal tan squared theta, okay? Let's look at two more that aren't too bad. There may be a little more involved, but nothing too crazy. I have faith that we can do this. So for example, 4 of the directions are the same. It says prove each identity, okay? And remember our tips that we can use is always start with the kind of the nastier side, the side that just has more going on. So that is definitely going to be the left here. And what our ultimate goal is we want to get the left to truly equal secant of theta. So this is our goal, okay? So what in the world could we possibly do to make this happen? One of the tips we have is sometimes it can be really, really helpful to write things in terms of sine and cosine, okay? We just We like working with sine and cosine, okay? And there's a way to basically convert all of the trig functions that are not sine and cosine into something involving sine or cosine, either using a reciprocal identity or a quotient identity. So getting things in terms of sine and cosine, it's a common practice, okay? So the very first thing I see is on the left-hand side, inside parentheses, I have cotangent of theta and tangent of theta. And remember, we have the reciprocal identities. The reciprocal identities state that tangent of theta equals sine of theta divided by cosine of theta, and cotangent of theta equals cosine of theta divided by sine of theta. So let's use that. Let's rewrite this left-hand side on the inside of parentheses. Let's rewrite those in terms of sine and cosine. So I'm going to keep my sine of theta that's outside the parentheses. And then inside parentheses, cotangent of theta, I'm going to write as cosine theta over sine of theta. And then tangent of theta, I'm going to write as sine over cosine. So sine of theta over cosine of theta. And know that our ultimate goal is to get this to somehow equal secant of theta. Okay, well, this is great. Now what? Well, let's see if we can distribute and essentially, ultimately, we'll say, get this into a single fraction. That was one of our steps. See if, when you start on the nastier side of the equation, see if you can manipulate it and get it into a single fraction. So we want to first distribute and then see if we can get a single fraction by finding an LCD. Okay, so when I distribute, hopefully this is obvious to you, but I'll go ahead and write out the steps. I get sine of theta times cosine of theta over sine of theta plus sine of theta times sine of theta over cosine of theta. Okay, well, let's see if things simplify down. And what do we get here? Well, sine of theta divided by sine of theta, that just reduces down to be just 1. So I'm left with cosine of theta. And then on the right side of this fraction or this expression, we have sine of theta times sine of theta. That's just sine squared theta over cosine theta. Okay, well, that didn't seem to help a whole lot, but we can try to get this written as a single expression. So remember, if you have like two things that look like fractions, see if you can write it as a single expression. So if we do that, we need an LCD. And so think of cosine of theta as just cosine of theta over 1. So I can multiply cosine of theta by cosine of theta over cosine of theta. That would turn this 1 into that common denominator of cosine theta. So let's see what happens when we do that. Well, cosine theta times cosine theta is cosine squared theta. Cosine theta times 1 is just cosine theta. That's the first fraction. The second fraction is sine squared theta over cosine squared theta. And what I have here now is a situation where I do have common denominators. So I can write the numerators over just the common denominator. So I get cosine squared theta plus sine squared theta over cosine theta. And please fix this. I noticed I put a cosine squared. It should just be a cosine theta right here. So fix that, please. All right, well, darn, has this done anything for us? And it may not look like it, but actually we're really getting somewhere, because if we go back to the Pythagorean identities, we have this one right here. Let me erase some of our side work. So we have right here that sine squared theta plus cosine squared theta is equal to 1. And that's exactly what we have in our numerator. So we can change out the cosine squared theta plus sine squared theta. And where are we at right here? Say that just equals 1. So this is really 1 over cosine theta. And what is 1 over cosine theta? Remember your reciprocal identities. 1 over cosine is equal to secant theta. And there you have it. Okay. So I want to make sure we write it really, really clear. We get secant theta equals secant theta, and that is our ultimate goal. So we were able to prove that this wacky left-hand side really did equal just secant theta. It took some work, but we were able to do it. Okay. So now let's look at part B. Now with part B, we have kind of an equal size mess. The left is as messy as the right, okay? So in this case, just pick a side. Let's say we make tangent to the fourth of theta plus tangent squared theta. Let's say this is our goal. So we're going to work with this side. We're going to work with the secant side and see if we can simplify the secant side down to something that looks like tangent to the fourth of theta plus tangent squared theta. Okay. And if I look at this left-hand side, I see a GCF that I could factor out. So always remember, you've got these these tricks up your sleeve. So you can multiply by a well-chosen one. You can write as a single fraction. You can also try factoring. And so in this case, I'm going to factor out a GCF of secant squared theta. Whoops, let me do this in let me erase and then do this in the black pen. So I'm going to factor out secant squared theta. When I do that, I'm essentially dividing both of these terms by secant squared theta. And what I get is secant to the fourth of theta divided by secant squared theta is just secant squared theta. Pretend secant squared is, or secant to the fourth and secant squared is x to the fourth x squared. How would those simplify? They would simplify to x squared or secant squared. And then secant squared theta divided by itself is just minus 1. Well, remember I told you anytime you see a trig function squared with a 1, think about that, okay? Because that might equal something really great for us. So let's go up to those Pythagorean identities and let's see what we can do. So we have secant and we have tangent. And from an earlier example, we already found that if we took the original identity and we subtracted 1 from both sides, we got that tan squared theta equals secant squared theta. And then the original identity tells us that secant squared theta is equal to tangent squared plus 1. So let's see if we can rewrite the secant side using these tangent identities here. So we're going to use the Pythagorean identities. We already know these have been established. We were able to prove them in a previous section. We can use these. Okay, so down here we have, well, secant squared theta. We know that that is actually equal to tangent squared theta minus 1. Okay, so that was one of the things that we were able to find. So secant squared theta equals tangent squared theta plus 1. Don't put minus 1, put plus 1. And then we were able to find that if we take secant squared theta and subtract 1, that's just equal to tangent squared theta. Okay, so that's from that first page of our notes with those identities. And I can just multiply here. I can basically take this right here and distribute it through here and here. Okay, so let's take tangent squared theta times tangent squared theta. Well, that's tangent to the fourth of theta. And again, if that's confusing for you, think of what would like x squared times x squared be? That would be x to the fourth. Well, tan squared times tan squared is tangent to the fourth of theta. And then I want to take tangent squared theta and multiply it by 1, where I get plus tan squared theta. And if we look, that is exactly our goal. So we were able to prove it. So use those fundamental identities of trigonometry as much as you can because they're already established. We already know they're true. So we can use them as fillers here when we get to a point where we're kind of stuck. See if you've got an identity that already works. Okay. So there you have it. We have used a lot of the tips and tricks. We've looked at multiplying by the well-chosen one. We've looked at getting a common denominator and writing things as a single fraction. We've looked at factoring. We've done all sorts of stuff here. So remember, be willing to try stuff. And if it doesn't go anywhere, go back to the drawing board and start something new. Use pencil, give yourself lots of space. Okay?